Hello, everyone. I am Liu Ruiqin from the MSTP LMT department. I'll introduce the synchronization technology in this course. First, I'll introduce the basic concepts of synchronization. Synchronization includes clock synchronization and time synchronization, which are also known as frequency synchronization and phase synchronization, respectively. Synchronization indicates that the frequency or phase difference between communication devices must be within a reasonable error range, so that all devices on the communication network can work at rates with fixed relationship. If the frequency or phase difference is out of an allowed error range, bit errors and jitter may occur. This degrades the transmission performance. Clock synchronization indicates that signals have a constant phase difference and clocks run at the same frequency. Time synchronization indicates that signals have a fixed phase difference of 0 and clocks run at the same frequency. In this course, I'll introduce the following clock synchronization technologies. 1. SDH, physical layer clock synchronization. 2. Synchronous Ethernet. 3. 1588 version 2. 4. CES ACR. SDH, physical layer clock synchronization, is a clock synchronization technology applicable to the SDH network. It implements clock synchronization hop by hop. Devices can extract clock signals from an external clock source, line clock source, or internal clock source. Clock sources can be traced properly after physical clock synchronization is implemented in master-slave synchronization mode. In this mode, clock source priorities are specified to ensure that clocks are traced level by level. On a network, the clock with the highest priority is the master clock. The master clock uses multiple backups to improve reliability. The standard SSM protocol carries the clock quality level to ensure that a network device automatically selects the clock source with the highest quality and priority. This prevents mutual clock tracing. Huawei Extended SSM protocol introduces the concept of the clock source ID. Based on this ID, a device determines whether a clock signal is sent from the local station. If yes, the clock source is considered invalid to prevent clock loops. Normally, the local clock of a device traces the signal of the master clock. When the external input clock reference is lost, the device takes the reference signal saved before the loss of external input clock reference as the timing reference. In this case, the clock enters the handover mode. However, if no reference signal is saved before the loss of external input clock reference, the clock enters the free run mode. Synchronous Ethernet is a clock synchronization technology applicable to packet networks. It implements clock synchronization hop by hop. Synchronous Ethernet is a technology for synchronizing clock frequencies over the Ethernet physical layer. It extracts clock signals from serial bit streams on an Ethernet line. Its working principle is similar to that of the SDH physical layer clock synchronization technology. Clock signals can be extracted from an external clock source, line clock source, or internal clock source. The clock source can be traced in master-slave synchronous mode. Standard and extended SSM protocols are supported to prevent mutual clock tracing and loops. The slave clock working modes include the tracing mode, holdover mode, and free run mode. Service traffic is mapped to PHB service levels by using traffic classification. Service QoS scheduling is implemented by using traffic policing, CAR, queue scheduling, SP plus WFQ, and congestion management, WRED. CES ACR is a clock synchronization technology applicable to packet networks and uses the adaptive clock recovery, ACR, technology to recover the clock synchronization information transmitted by CES services. CES ACR is a non-per-hop clock synchronization technology. The source end, master, considers the local clock as the timestamp in the RTP packet header and encapsulates it in the CES packet. The sync end, slave, recovers the clock signal according to the timestamp in the packet and traces the clock signal. Delay variation, route changes, and packet loss of intermediate networks affect the quality of the clock signal recovered from CES packets. Smaller delay variation, route change, and packet loss ratio indicate better quality of the clock signal recovered from CES packets. IEEE Standard 1588 version 2 is a clock and time synchronization technology applicable to packet networks. It traces clock and time hop by hop and implements time synchronization with sub-microsecond precision. Now, I'll introduce working principles of IEEE 1588 version 2 from the following aspects: clock time source, clock model, master-slave synchronization mode, and delay measurement. A device that supports IEEE 1588 version 2 is defined as a PTP device. A port that supports the IEEE 1588 version 2 protocol on a PTP device is defined as a PTP port. By using IEEE 1588 version 2, devices can extract clock signals from an external clock source, internal clock source, synchronous Ethernet clock source, and PTP port clock source. Extract 1 pp/second plus TOD time signals from an external clock source, and extract time signals from the PTP port. The synchronous Ethernet technology is used to implement clock synchronization on OSN devices. Then, IEEE 1588 version 2 is used to implement time synchronization on OSN devices. Clock modes of IEEE 1588 version 2 include OC, BC, and TC. An OC has only one PTP clock port, which can be used to obtain clock signals from the upstream equipment or distribute clock signals to the downstream equipment. A BC clock has multiple PTP clock ports, one of which can be used to obtain clock signals from the upstream equipment, and others are used to distribute clock signals to the downstream equipment. A BC and an OC need to be synchronized with other clocks, but a TC does not. A TC has multiple PTP clock ports. These ports transparently transmit time signals, forward only 1588 version 2 packets, rectify forwarding latency, but does not synchronize the time. The TC is not supported by OSN devices. PTP ports use the master-slave mode to trace clock signals. A time synchronization network can be regarded as a spanning tree, of which Grandmaster is the root node. All nodes on the network are synchronized with Grandmaster. The PTP port has 3 states that can be used to determine the master-slave relationship of clocks. Master. For a pair of PTP ports between which time synchronization is performed, the upstream port distributing clock signals is the master port. Slave. For a pair of PTP ports between which time synchronization is performed, the downstream port receiving clock signals is the slave port. Passive. Indicates redundant ports generated after the clock synchronization spanning tree is determined on a PTP network. These ports neither distribute clock signals nor are in synchronization with the master port. When the network topology is changed, a passive port may be changed to a master or slave port. Manually specifies the PTP port state to implement the master-slave hierarchy of all clock nodes. Each clock node runs the best master clock, BMC algorithm to automatically determine the master-slave hierarchy. Delay measurement has 2 modes, end-to-end and peer-to-peer, which are also known as delay and P-delay. The difference between delay and P-delay modes is as follows. In 2-step mode, the packet exchange modes are different. Now I'll introduce details of the delay measurement mechanism. First, let me introduce packet exchange modes, 1-step and 2-step. 1-step indicates that sync packets in delay mode and P-delay response packets in P-delay mode carry the timestamp of the packet transmit time. 2-step indicates that sync packets in delay mode and P-delay response packets in P-delay mode do not carry the timestamp of the packet transmit moment. Instead, the devices only record the sending time of the packet. The subsequent packets, such as follow-up packets and p-delay response follow-up packets, carry the timestamp of the packet transmit time. Now, let me introduce the delay measurement mechanism in one-step mode. As follow-up packets are used in two-step mode, they are not involved in this introduction. In delay mode, the master port sends a sync packet that carries timestamp T1. Then the slave port receives the sync packet and generates timestamp T2. The slave port periodically sends a delay request packet to the master port and generates timestamp T3. The master port receives the delay request packet, generates timestamp T4, and then sends the packet back to the slave port. Then the slave port obtains timestamps T1, T2, T3, and T4. TMS equals T2 minus T1. TSM equals T4 minus T3. TSM and TMS are values of bidirectional delays, which are assumed to be the same. The delay between the slave and master ports is half of the sum of TSM and TMS. That is, T2 minus T1 plus T4 minus T3, and the sum is divided by 2. The slave port adjusts the local time according to the calculated delay to implement time synchronization with the master. In p-delay mode, the method used to obtain all timestamps is similar to that in delay mode. IEEE 1588 version 2 time synchronization requires that the bidirectional delays of a link are symmetrical. Otherwise, the algorithms of IEEE 1588 version 2 time synchronization cannot be implemented. However, the bidirectional delays of a link are asymmetric and need to be corrected. Asymmetric delay may be caused by factors related to links, such as length difference of the cables in the two directions. Time difference may also be caused by factors related to equipment, such as difference in processing from the generation of a timestamp to the link. The delay compensation value delta T needs to be tested by using a meter or calculated according to the cable length. OSN devices support two-fiber bidirectional ring network automatic compensation after a fiber cut is repaired and single-fiber bidirectional automatic compensation. The table in this slide shows the accuracy of clock synchronization. The table in this slide shows application scenarios and characteristics of the clock synchronization technology. That's all for this course. Thank you.